and splitters slash dividers. Now, most people are familiar with these two things right here. Where do you see this, by the way? A splitter or divider? I'm sure a lot of people in here have done this. Anybody? Cable. You put splitters in your house all the time, and all the time, bless you, to do one single thing, to make sure that you can get some signal onto one TV or computer and some signal to another TV. Right? You've done it. I'm going to start off by talking about couplers first. We'll work with splitters, then couplers and splitters. We're going to start with a general coupler. And last time I talked about this. When I talked about a coupler, this is going to be a 3-port device. And I'm going to draw it as a circle the way Dr. Wentworth's book does. He shows it as a circle. Here, he's talking about port 1. This is port 2. This is port 3. Now, in port 1, we know we have V1 plus coming in. We also have a reflected signal. That's V1 minus. Here we have signal coming out here, V2 plus, or excuse me, V2 minus. We've got a signal coming in, V2 plus. And here we have a signal, V3 minus. We have a signal coming in, V3 plus. All these may or may not be there. And this is in a very general sense what's going on here. Now when we have this, suppose I wanted to define a coupler such that I had all the incoming portions of the first signal to go out port 2. And then I wanted to have all the signal from port 2, incoming signal from port 2 to come out port 3, and all the incoming signal from port 3 to go out this way. Now this is fixed, but this is where it's used. Any type of system that uses duplexers or like radars, for instance, you have signal going out and coming in on the same antenna. You want some of that signal to go, you want the signal going out coming from one source. As the signal comes back, it splits or it's going to be divided. Really, it's going to be coupled to a different system. Does that make sense to everybody? You have to have some power going out the antenna. You don't want any of that circuit coupling energy to the circuit that's going to actually decompose the signal. So if you have this, I'm going to start by setting up the equation. V1 minus would be equal to, and the general way we did it was 2 by 2. You always start with S11, that's the reflection coefficient, times V1 plus. Then it's going to be plus S12 times V2 plus S31 times V3 plus. We're going to start here. When I look at this, now follow me on this class. I want only the signal from port 3, the incoming signal from port 3 to come out port 1, right? Does everybody see this? Go, if there is something wrong, let me know.
It should be S13.
Or S13, pardon me, you're right. Thank you. S13. S13. If I take a look at this, and I come from port 1 to port 2, and I want that, well, really, does this term matter at all? We don't really want any of V1 coming back, right? So ideally, this reflection coefficient right here would be 0. Here, we see for S12, we don't want any of V2 getting back out port 1, right? Take a look at that for a second. Are you all right with this, Emma? So this would be 0. Here, we want all of V3 to come out port 1. So this would be a 1. Now this is ideal. You'll never get these values. What you're going to get is something like that. You'll probably have a very low value of a reflection coefficient. This would be a coupling coefficient, and this may be something that's, I don't know, 30 dB below what it should be. In other words, 1,000 of the signal to get out. Now, everybody can see that at least this fulfills the request that everything from port 3 comes out port 1. Does that make sense to everybody? Let's go down to the next one, V2. V2 minus. When I take a look at this, this is going to be S21 times V1 plus, and this is S22 times V2 plus S23 times V3 plus. Everybody with me on this? Now when I look at this, for V2 minus, I only want a signal from V1 to get out on that port. Does everybody see that? So the only thing I'm going to do is make this S2101. Here this is going to be a 1. This will be a 0, ideally. This will be a 0. Now if you want to, you can just put these values right below there. Everybody all right with it? I hope they're seeing this. It should be clear. I'm making this as simple as possible. For V3 minus, here we're going to have, I like to do this. When I look at V3, I want only the signal, incoming signal from V2 to get on there. And I can see that makes this a 1. Matter of fact, what I'll do is just put a 1 down here. And these makes these 0. Can everybody see the way I've done that? Now, I will give you, on an exam, I will give you some arbitrary conditions. And we're going to talk about one other set of conditions. We're going to just work through it as a class. And if I generate this S matrix for this, what would it be? Here, I start off, I have 0, 0, 1, 1, 0, 0, and here it's going to be 0, 1, 0. That would be the S parameter matrix, ideal S parameter matrix. You may want to write that down. This is ideal. Ideal S parameter matrix for this set of conditions. Now I have a question for everyone. What will happen if now I change this a little? I'm going to let you copy this down. I'm going to change this thing right here. Does everybody have this down? Some people are still copying. It's not hard, and some people have already seen this. Whenever you want some V of n minus, it's going to be equal to some S of n comma m times V of m plus. Well, this is going to be the S parameter that couples it. If you want it to be 0, n can be anywhere from 1 till 100, or any number of ports, but really we'll limit it to 1 to 4, really 1 to 3 for the test. If I have that, whatever I want coming out, the S parameter that would have to do with this number, say it's 2, and the coupled signal from the incoming port, say it's 3, 2, 3. If this was the third port, the input to the third port coming out of the second port, then S23, or excuse me, yeah, S23 would be 1. Does everybody see this, class? It's simple to do. But if I have this and I change it, just to make sure you see this, what if I wanted to do this? I wanted to couple port 1 this way, I wanted to couple port 2 that way, and that was it. How would you do that? Well, here, what would you start with? If we didn't want to do the whole matrix, where would you start based on what I showed you right here? Well, we want V, what port are we coming out?
3.
Can everybody see it? Yeah, V3. V3 minus. Now, where do we want the signal from to get coupled to? From port 1, right? So this would be S31 times V1, excuse me, V1 plus. This would be S31 times V1 plus what else? We'll put the values down in a second. Here it's going to be S32 times V2 plus. Both of these values would be 1. 3,1 and 3,2, everything else in that matrix would be 0. It's very easy to do. I'm going to warn you about one thing doing these things. You're going to look at this, or take a look at this thing, and you're going to see some couplers in a second, and all of a sudden you're going to notice that these off-term numbers are not 0. The reason is it's not ideal. Or, in fact, maybe you want some of the signal coming in from one of these ports, a very small amount of signal to come out a different port, not where the main coupling is. And there's reasons for all of this. So just remember that. That's the coupler in a nutshell, and it's ideal. It's not hard to do. You try a few, you'll get it, I'm sure. I'm going to see this so far. Any questions at all about this? All right, next. Next, we talk about dividers. We're going to start with a simple divider. Has anybody ever opened up one of those dividers? Have you looked at it? What's inside of it?
Coils?
There.
Talking about a coax?
Well, there's a coax cable that ties into both ends, but inside, did you see a small capacitor, coil, small coil?
I just saw two small coils. I didn't see a
All right,
capacitor.
I think there's a capacitor. That's a type of match. Well, actually, I'm not going to even start on that one right now. But there's only some very small passive elements. That's what I'm getting at. It's very inexpensive to do these things, but you will get some loss. The first thing we're going to talk about is a standard resistive divider. Now, when we talk about a resistive divider, this is the cheapest or least expensive. But it also has the most loss. Now, with all these dividers, there's one key thing you want. You want the reflection coefficient, or S11, comma, reflection coefficient of port 1, port 2, S22, and so forth, to be equal to 0. You don't want any reflected signal. You want it matched, in other words. Whatever it goes down into one of these couplers, you don't want any signal being reflected back. So that's the idea behind it. Now, with that in mind, what's the cheapest one? What does the cheapest one look like? Well, you start out, and you have some cable that's got Z0. Now we're going to take this signal. We're going to assume the signal's coming in here. It's going to be some V1 plus. You can call it V1. Now what we're going to do with this signal is first, we start adding components. So now we get these pieces of wire and we add a resistor here. This is going to have, excuse me, let me get this right. Draw that straight. We add a resistor here. This is going to be a value of Z0 divided by 3. When we get to that point, then we break this off and we add another resistor, Z0 over 3. And here's where the split occurs, or it divides. Here we have Z0 over 3. Comes down here. Now it comes off, and you have have Z naught here, and you have Z naught here. I'll let you draw that. Really what I'm trying to indicate is you got one coax cable or transmission line that comes off and divides into two transmission lines with 3 resistors in between. Does everybody see that? Make sure you draw this down. It is in the book, but there's going to be things that you will wonder about, possibly wonder about. This is not hard to understand what goes on. We're going to start with this segment right here, this portion right here. Now when I look at that, what you actually get for the input impedance right here, looking that way, what would it be? If I look at that, don't I have Z naught divided by 3 into a characteristic impedance of Z naught? So couldn't I put a simple resistor there to represent that value of Z naught, class? How many see this? Sure, if you have a coax cable, say it's 50 ohms, and you put a 25 ohm resistor in series with that, when you look into that, you get an impedance of 75 ohms, don't you? Does that make sense to everybody? Now what about this side right here, when I look this way? What do you get? When I look this way. Think about it. I have that resistor in series with this resistor, don't I? How many see this, class? Fellas in the back, can you guys see it? And if you can see it, I don't know if you can or not, I hope you can, but if you can see it, obviously you can see what I'm doing here. Now I've got the same system, and the only thing that's happening here is I have Z naught over 3 and Z naught. Well, what's the net impedance going into this section right here? Take one look at it. What would it be? Just these two right here. 50. It's going to be 4/3 Z naught, right? What about this right here? Isn't it the same? Sure. So really what I have is 4/3 Z naught in parallel with 4/3 Z naught. Those two are in parallel, and they're going to be in series with this Z naught over 3 term, this Z naught over 3 term. I'll draw it over here. This is Z naught over 3 in parallel with 4/3 Z naught in parallel with 4/3 Z naught. Means the input impedance right here, Zn, is equal to, this would be 2/3 Z naught if we looked at the total. You all agree with that? The two parallel resistors are going to have an equivalent of 2/3 Z naught plus 1/3 Z naught is going to be simply Z naught. That's the key. With that, we know what we've got there is something that's going to be impedance, or looking in here, I have an impedance of Z naught, correct? What's the reflection coefficient looking into this point right here? In port 1, if I'm looking into a value of Zn equals Z naught, class, what would it be? How do I calculate it? Always. I take the input, or the impedance I'm looking into, Zn minus Z naught over Zn plus Z naught. Do you agree? For the reflection coefficient? Well, what's Zn? Just say it. Z naught. So it's Z naught minus Z naught, or 0 over 2 Z naught, or it's 0. Thus, no reflected energy. That's the idea behind this whole thing. The S parameter matrix for this we can get fairly easily if we want to analyze it. But what this matrix is going to look like in the book, if somebody can get the page number that's on, go ahead, but this is 011-101 and 110. That's what the S parameter matrix looks like for this one that I've shown you. Can you get this? This would be the S parameter matrix for the resistor divider. Now, if you wanted the insertion loss, here, take note. This is something people make mistakes on. When we do insertion loss, say for 2-1, insertion loss 2-1, write this down. Insertion loss is always going to be, it's always going to be looking at the S parameters. Now, what did the S parameters deal with? Or what does the reflection coefficient deal with? Power or voltage or current? Class? When I look at the reflection coefficient, what is the definition of reflection coefficient in terms of a fundamental, the fundamentals? What is that? Isn't that the ratio for the reflection coefficient for port 1 of V1 minus over V1 plus? Let me see that. You know that, don't you? That's the fundamental definition. Whatever the elements in the circuit are, they dictate what that value is. But that's the definition of this. When we look at this, this is a voltage, right? I'm saying this because in the last exam there were some mistakes made with dB. So I'm just going to get this out of the way. Here, insertion loss is in dB. But if we look at the reflection coefficient, not the reflection coefficient squared or the S parameters only, like 1, 2, would be equal to minus 20 times the log of the magnitude of S21. S21 has to do with how much voltage comes out of port 2 that was incident on port 1. That's a volt, that's 20 log. Is everybody with me on that? Now what if it was all of it? What if S21 was equal to 1? Everything out of port 1, or everything into port 1 came out port 2. What would that value be? It's 0, right? Log of 1 is 0. That means you have absolutely no insertion loss. You don't lose anything. Well, what if this value is a half? What do you get? What do you get? What is the insertion loss to 1 when the value is a half? It's minus 20 times log, that's log base 10 by the way, of 1/2. You can check this. It's going to be about 6.06 dB. Now on this one, for the S parameter matrix, you see the insertion loss terms that would be for 2-1, for 1-2, for 3-1, and so forth, all the way down here, or for 1-3, I'm sorry. If you look at all these values, they would be a value of a half, wouldn't they? Do you all agree? It's 1/2 times this. That means we have 6 dB of attenuation. That's a lot. We're paying for this divider, even though it's very low in terms of the expense we're spending, but we're paying for it in power. We're losing a lot of power, a lot of signal strength. That's how come this type of divider is something you use if really you got plenty of signal and you don't need to worry about the signal being reduced any further down the circuit. This would be something you could do. And it's very inexpensive, there's no phase problems. Really easy thing to do. That's 6 dB. But we can do better than that. We can actually get it down to only 3 dB loss for a Wilkinson divider. It's the last thing, well, I don't know if I'll be able to cover too much more new material. But this is a Wilkinson divider. Now, where are you going to see this? Well, how many are involved in any type, any single thing, is anybody doing anything with, let's see, microwave, RF energy, any type of wireless communications? Most of you, not most, a lot of you will work in that area. If you work in that area, you're probably going to see this stuff. You probably need to be aware of it. At least at some point, I think you'd see it. because this is real hard learning. This is where we take theory out of the classroom, and we actually talk about devices. Talk about things with faculty. So now, when we take a look at a Wilkinson's divider, I want to make mention of one other thing before I do. There are so many different types of dividers, it's not even funny. Have you got this in your other classes, by the way? Any type of dividers? Analog? No? Okay. Lots of stuff on dividers. A Wilkinson divider fundamentally comes in, and you have some characteristic impedance Z0 here. Now, start off, come to this port right here. Now what happens is, this is a divider, remember, a splitter. It's not a coupler. We're not doing one of these things. We're running energy in one port, out the other type deal. Now we come in and we make this a quarter wavelength long, lambda over 4 long. This would be the same distance. The characteristic impedance of this is square root of 2 times Z0. Now there's going to be another arm of this coming down this way. I'm trying not to make this too confusing, but it's going to be inevitable. Here, this is going to be quarter wavelength, and the characteristic impedance here would also be square root of 2 times Z0. Now this is one other thing that happens. And I'll try to draw this in here. I'll get out of your way in a second. If somebody wants to give me a page number where this thing's shown, I'd appreciate it. Because frankly, this drawing, port 1, port 2, port 3. It's in the book, but I don't know what gauge it's on. When I look at this book,
570.
it's on 570. There's one other thing that happens.
571.
571. You're going to have a resistor right here. It's going to be between this and this terminal. And it's going to have a value of 2Z0. Now, if you just write down that page if you can't see what I'm drawing here, but really I'm just putting 2 quarter wavelength section, or quarter wave sections in there, each with a characteristic impedance of square root of 2 times Z0. When I do that, and I add this resistor, what effectively happens is the S parameter network can be given. There's one slight difference. The S parameter network for this is going to have a minus J over the square root of 2. Then it's going to have values here. I want to make sure. He's going to throw 1, 1. This is 1, 1, 1. I believe that's it. Sorry, this is going to be a 1. Now the reason I'm going to mention the Wilkinson divider, we're going to see something on this, and this is the important thing. You can look at this drawing up in the book. But for a Wilkinson divider, that being the S parameters for it, if we look at the insertion loss on the 2-1 term, in other words, the insertion loss for this term right here, that would be S21. That times square root of 2, or divided by square root of 2 times minus J. Here we would have minus 20 times the log of the magnitude. Remember, that's magnitude of minus J over the square root of 2. And I'll tell you what happens. People forget the magnitude. What's the magnitude of J or minus J? Anyone? In the back. What's the magnitude of J? Think about J. What does it mean? 1 at an angle of 90 degrees. What's the magnitude of that? Just the magnitude. Does everybody know it's 1?
Yes.
Value is 1, magnitude is 1, so this is really equal to minus 20 times the log of the magnitude of 1 over the square root of 2, and that is going to be minus about 3.03 dB. Here we reduce the loss by 3 dB by simply adding a quarter wavelength section with that increased impedance and putting a resistor on there. Now, working the actual S parameters for this matrix is a little hard. I don't have time to go through working some of these S parameters. But now, I'll give you some homework with these things. It's not going to be hard. And I'm not going to go through the coupler section on this. I wanted to start in, first of all, if you have any questions, ask them now. This is the last stuff we covered. Yeah, Josh?
The square root of 2 Z naughts, are they just on 2 sections there? Is that what you're trying to say?
Yeah, if I drew this up and just put straight lines here,
Okay.
what you would actually have is a characteristic impedance of Z naught.
Yeah.
Then you would have a characteristic impedance here. First of all, this length would be lambda over 4. This characteristic impedance would be square root of 2 Z naught. And you have another line down here. This characteristic impedance here would be square root of 2 times Z naught. This length would be equal to lambda over 4. And if you come out to this point, you tie a resistor between the terminals, these two terminal sets, from the top, it's got to be the same positive terminal, or the same nut at the ground. It's going to be equal to 2 Z naught. Then this speeds off right here to a characteristic impedance of Z naught. Now, that's the important point, that you lose less with this. But they're all passive elements. The only thing we've done is add one resistor, and now we're using a quarter wavelength section. What happens with the Wilkinson divider that didn't happen with the resistor divider? Can anybody see that? Think about something that has to do with the application of this. Suppose I try to use this, suppose it was for 75 ohm cable, for charter cable, and I used it with 75 ohm cable, but it was being used in a different frequency band. What would happen? Anybody? That's right. This would no longer be a quarter wavelength. That's a physical length. That quarter wavelength is only true for one frequency. So a Wilkinson divider, another downside of it, even though it's a little more difficult to fabricate, it works on a very narrow frequency range. Keep that in mind. Those are the two things. The resistive divider is wideband. You can use it at any frequency. Does everybody see that? I know this seems kind of dry until you get some threatening problems that make you think. But it is necessary that you know this. Now we start into the review. Now, in the final EMAG for this class, it's comprehensive. You're going to get stuff on electrostatics. I'll put it down, don't worry. You're going to get electrostatics, magnetostatics. You're going to get a Smith chart problem. Possibly. Smith chart problem, and you're going to get something with fields. Go ahead, Drew.
Can you post some notes on the review?
I'm going to say, I'll tell you exactly what the sections are. But I got to start somewhere where I think there's some areas of weakness. Smith chart, I think you guys at least have a good handle on what it is and what it can do for you. We haven't done any stuff tuning in a long time. But we're going to start with some basic stuff. Remember this, electrostatics really is the underpinning, or understanding EMAG 1 is the underpinning for so much of what we do here. Even though this is stuff that's varying in frequency, understanding Maxwell's equations is essential. And I'm going to put them up here because that's where everything starts. When we deal with Maxwell's equations, everybody knows these are the fundamental laws. They're based on experimental observation. As far far as we know, these things work in every domain, with one, maybe one exception. And that would be at extremely high levels of gravity, if you're down in a black hole, but even then they can't work. When we look at this, curl of E is equal to minus dB dt. And really the first one is curl of H is equal to J plus the partial of D with respect to T. These are the two. I'm putting them up as high as I can. Here, there's some basic concepts you have to know. J is equal to sigma E. D is equal to epsilon E. B is equal to mu H. These are the equations that couple this. It couples the actual current density to the electric field strength with the conductivity, the D field from the E field with the permittivity, the B field from the H field with the permeability. These are essential. Now, I know you're going to get a formula sheet, so you may just say, well, I don't need to know these. You're going to need to know them if you need to know how to work problems, because you'll need these things. Now, when we deal with this, one of the things that we deal with, we start out by electrostatics. That's the full set. We start out by saying the E dt and the B dt equals 0. By the way, what's the one thing I left off here that's a fundamental equation that has to do with a fundamental law? The guy's name begins with G. Gauss's law. What is the point form of Gauss's law? Does anybody recall? Divergence of D is equal to rho V. Remember this? Volume charge density? And if we stick in for D is equal to epsilon E, we get divergence of E is equal to rho V over epsilon. Now really, that in a sense, is pretty much what we need. From there, we can solve, theoretically at least, any problem. Coulomb's law is not clear in this, but we could get it. We'll write that down. Start with these Maxwell's equations, and let's do one thing. When I deal with electrostatics, how do you start this? And this is what Coulomb's law is. How do I do a problem where I just have single points of charge, 3 charges, Q1, Q2, Q3. I have R1, R2, R3. These are vectors. How do I get, first of all, the electric field here, class? How would I get the electric field? It's the easiest way to do it. It would be simply a sum of Q1 over 4 pi epsilon naught R1 magnitude squared over AR1 plus Q2 over 4 pi epsilon naught over magnitude of R2 squared AR2 plus Q3 over 4 pi epsilon naught magnitude of R3 squared AR3. That's a vector form. I could write it as a summation. I prefer to do it this way. That is a vector equation. Yes?
Is that the voltage or the E field?
R squared would be volt, or would be the E field. If it's R, 1 over R, it's voltage. We're going to get there in 1 second. Remember, force is always proportional to R squared, 1 over R squared. Now, if we want the voltage, we assume the voltage as R goes to infinity, and you might as well set a point, some origin, call this point 0, 0, that point R. But if the R, as R goes to infinity, if the voltage is 0 volts, then you could say the voltage at this point here, and I'll just call it the observation point, 0, would be equal to Q1 over 4 pi epsilon, and this would be R1 plus Q2 over 4 pi epsilon naught R2 plus Q3 over 4 pi epsilon naught R3. And the point I'm going to make here in a second is an important one. When I do that, there's two things you see different about this. Well, really, one thing in particular. Look at the E field for a second. The E field is a vector. There are 3 components, there are 3 vector components, a total of 6 components that you have to add. How many see this right here? There are 6 total field components. They require vector addition. There is no phase information here. Here, there are only scalar quantities, and there's only 3 of them. Does everybody see that? Only scalar quantities. Only 3 of them. The voltage is much easier to get. That's my point on this. Now, the reason I went through this, because some time ago I gave a little problem like this on the final, and a lot of people got it wrong. They didn't remember this stuff. That's the reason I'm putting this up there. That's voltage and electric field from point charges, right? Now, if I wanted line charges, or any other form of a charge, how would I get it if I had a line charge here? I had some line charge starting at 0, going at L, on the z-axis. And suppose, for starters, I want the electric field at this point. Ideally, how would you get it? I didn't even put down the fundamental law that is applied to these things. Well, what do we look at when we do this thing? We take a look at a differential electric field here, and we say if we have a differential amount of charge right here, we have some dq. From that differential amount of charge, if we come out and we're a distance r away, we can find the differential electric field here. I'm going to erase this for you. I can say that this would be equal to simply dq over 4 pi epsilon naught, and here we're assuming epsilon is equal to epsilon naught unless otherwise stated, over, and it would be r squared AR. Got 2 questions for you. That's the differential electric field. I didn't even get to what R is. We'll come to that separately, and we'll deal with that in a second. First of all, how do I get AR if I have R? If I have vector R, right here, that's a vector. What is AR in terms of vector R? Does anybody recall? These are the things that people have problems with. Vector. If we want a unit vector in the direction of R, isn't it R vector over the magnitude of R? Y'all remember that or not? How many do? Okay, a lot don't. This is usually not a problem. That is. Couldn't I rewrite this then and say that this is really equal to dq over 4 pi epsilon naught times, really it would be r vector over, and this would be r cubed. That's an easy way to do that. Now we can do that. See it all right? All right, now that's easy to do. What is dq though? When I deal with dq, we've been talking about all sorts of stuff before, but we haven't done this in a while. We talked about differential charge, differential surface charge, line charge, all sorts of stuff, right? Volume charge, but it's always going to be the charge density in the respective frame. If it's volumetric, it's 1 over volume squared times charge. If it's going to be something where it's line, it would be charge per unit meter, or rho L. Then it's going to be times, rho L times DL, and that would be DQ, that would go up here. Now, I'm setting this up because next time I'm gonna do some problems. You got a question about it?
Yeah, I got into this a little late. That's DE up there.
Differential electric field.
Yeah, it just looks like a circle. I'll make sure. Appreciate that.
We get that, and we have these things. Still kind of abstract. How many at least remember this from EMAG 1? We did this stuff, right? We did all this stuff. Remember we did this for a long wire, and then we did a circular loop, and then we did a plane. We did all that stuff. By the way, without getting this is where we're going to stop right here. What is the electric field? When we look at the electric field, what is it for an infinite length line? If the line is infinitely long on the z-axis and I'm out a distance, rho away. Here, rho becomes my r vector. When I'm out a distance, rho away, and I wanted the electric field, do you remember what that is, anybody? Anybody at all? One person? That was equal to rho L over 2 pi epsilon divided by rho. This is the charge density. And the A rho direction. How many remember that now? Remember seeing that? It always varies as 1 over the distance from the line divided by 2 pi epsilon weighted by the charge density. And it would be radially away. Remember doing this? All right, that's what it is from a line. Does anybody remember what it is from a plane? If I have a plane here, and I say that this is an infinite plane, and I'm some distance z above it, or call it h above it, and I want to know what the electric field is here, and on this plane I have some surface charge density. Hopefully this will refresh your memory, so next time when we start on this, I won't be dealing with a blank slate. Right here, what is that value of the electric field if I'm h above it? Does anybody recall that?
It's like
Couldn't hear you.
1/2 charge.
You're actually, it's going to be rho s divided by 1/2 epsilon naught. That's right. And it would be in the direction, if this is the z-axis, it will always be in the direction perpendicular to the actual infinite plane. Now, next time what I'm going to do, I'm going to give you a heads up. You're going to get some homework today. I'm going to go through one, maybe two of the homework problems quickly. I'm going to tell you to do them. Don't skip on this one. Second thing is we're going to start the review. We're going to start with electrostatics. I'll put down the fundamental stuff on electrostatics. We're going to go through there. We're going to go through magnetostatics, and I'll tell you what you need to know. When we leave, you'll know what you need to know, all right? Now, please, next class period, there are no late projects. When you come into class, by the time I leave, that seals the envelope, that's it. If you don't hand it in, that's it. So you either get it to me before or in that class. I'm not be late.